Hello guys, welcome to the first introductory video of our topic LIGO and the discovery of gravitational waves. Here we will discuss in detail what are gravitational waves, what is LIGO, what is advanced LIGO, and LISA, the successor of LIGO. We will be learning about these topics about a series of 4 video lectures. So let us begin our first chapter. Chapter 1, Gravitational Waves. So, gravitational waves are simply disturbances in the space time fabric, or we can say ripples in the space time fabric, propagating at the speed of light. They are emitted by bodies having accelerated masses. Some of the possible sources of the gravitational waves, according to the current studies, are supernova collapses of stars. When a very big star, much bigger than our own sun, when it goes supernova, in the core remnant of it, a black hole is formed. So the supernova of collapses of very big stars can cause gravitational waves as according to the current observation. Collisions of neutron stars and black holes. So as you can see also in the given pic, we can see that how two black holes are orbiting each other, and in the course of orbiting each other they are emitting huge gravitational waves. And same is the case with neutron stars. When two neutron stars are about to merge, in the ever in the overall dancing of their mergers, they emit gravitational waves. And other possible sources may be from early universe, those we don't know about. So some of the properties of gravitational waves are: they travel at the speed of light, they can go through any medium, they warp the space-time fabric, and they carry information of their violent origin. So in the in this current slide we will see how the a plus polarized gravitational wave and a cross polarized gravitational waves acts on a ring of particles. So let us see how a plus polarized gravitational wave will act on a ring of particles. And now let us have a look at a cross polarized gravitational wave. How does it will act on a ring of particles? So as we can see, as a gravitational wave will pass through an observer, in this case a ring of particles, the observer will find space-time to be distorted by the strain of the wave. Distances between objects will increase and decrease rhythmically as the wave will pass through them, at a given frequency corresponding to that of the wave. The effect of a passing gravitational wave can be visualized by considering a region of space-time such that it is perfectly flat, with a group of particles at rest lying in a plane. As a gravitational wave will go through the particles along a line perpendicular to the plane of the particles will follow the distortion on spacetime, oscillating in a cruciform manner such as that shown in the animations. The area enclosed by the test particles does not change, and there will be no motion along the direction of propagation. So the oscillation depicted in the animation are exaggerated for the purpose of discussion. In reality, actually, a gravitational wave has a very small amplitude as compared to the one depicted in the animation. However, they help illustrate the kind of oscillations associated with the gravitational waves as produced, for example, by a pair of masses in a circular orbit. In this case of amplitude of the gravitational waves is constant, but its plane of polarization changes or rotates at twice the orbital rate. And so the time varying gravitational wave size exhibits a variation as shown in the animation. If the orbit of masses is elliptical, then the gravitational wave's amplitude will also vary according to the Einstein's formula. So, let us see. So, here we will discuss about the history of the gravitational wave. So, they were first predicted by the Einstein in 1916 when he published his theory of general relativity. Later on, their existence was first proved by the Joseph Taylor Jr. and her colleagues in the 1970s and 1980s. Later on, Joseph Taylor and Russell Hulse discovered a pulsar orbiting neutron star in 1974. The pulsar timing observations over the next decade showed a gradual decay of the orbital period of the Hulse-Taylor pulsar that matched the loss of energy and angular momentum in gravitational radiation such as that predicted by the general relativity. So Taylor and Weisenberg in 1982 saw that the orbit of pulsar was shrinking due to the release of gravitational waves. That helped them earn a Nobel Prize in physics in 1993. So guys, thank you for watching the video. If you like the video, please press the like button and subscribe to our channel, The Galactocoaster.